Our last chapter was really focused around limits, and in this chapter we're going to start looking at differentiation, which will basically further our study of limits. So we'll begin by looking at the derivative and tangent line problem. Just as in our last chapter, I will break this into smaller videos, essentially one for each objective. We'll start by looking at the slope of a tangent line to a curve at a point. Then we'll look at the limit definition to find the derivative. Then we want to take a closer look at the relationship between differentiability and continuity. We're going to start by looking at the slope of the tangent line to the function f of x equals x squared minus 2x plus 1, and we're looking specifically at the point 3, 4. So we're always going to specify a point. And essentially what we're going to do is we're going to start by just finding the slope of the secant line. So again, we have some sort of quadratic function, and what we're going to do is we're going to continue to draw secant lines that we feel most closely represent the slope at that point, and we're going to look for that pattern. So for instance, I've done the first one for us. If I plug in 4, then I get an answer of 9. So my ordered pair here would be 4, 9. And the slope of the point is, because I already know it goes through the point 3, 4, I'm just using that slope formula that says take y2 minus y1, so that's y2 minus y1 over x2 minus x1, which gave me a slope of 5. So really what I'm looking for is I want to see what pattern is going to occur in this row. So again, I did all of this with a calculator, and I'm not going to, this would be a forever video if I went through each one with a calculator with you. But essentially, when I plugged in 3.5, so f of 3.5, easy to do in your calculator, I showed you last week, then finding the slope using the point 3.4 and the point 3.5, 6.25, I get a slope of 4.5. And then I just continued that process, and I want you to see what's happening as I continue down my table. And so even though I haven't found the slope here at 3, 4, I can pretty much determine that the slope is probably going to be 4. So again, using the table that we just created, it appears to us that the slope of the secant line at 3, 4 is 4. But we didn't really like making the table, so what we're going to start doing is looking at how to generalize that a little bit. We still will make a few tables, but before we continue, I want to make sure you understand the difference between the secant line and the tangent line. So remember that the secant line, and we talked about this last week, would be this line right here, which goes through 2 points, and it approximates the slope of the tangent line. And remember, as this point got closer and closer and closer to the point in question, the slope got closer and closer and closer to the actual slope of the tangent line. So that's important. It's also important to remember that we were finding slope using the slope formula. Oh, and again, the tangent line, of course, is the line that would just touch that point and then continue going. So again, how might we find the formula for the slope of the secant line to the slope of the tangent line? Well, we're going to start by just taking this formula and changing it using this notation. So let's talk about that notation. This first guy is at C, and then this is just f of C because we're saying plug it in, which makes sense. The next guy is at C plus delta x. Delta x is just code for the change in x. So delta x refers to how much change in x was there, which makes sense because that's what this is. It's the change in x. This guy up here is f of the C plus delta x. So it might look confusing to begin with, but it's really just using a different notation. So if I were to plug that in, I would say y2 is f of c plus delta x minus f of c over, my denominator would be c plus delta x minus c. And obviously that denominator, the numerator, there's nothing we can do about that quite yet. And the denominator, c's, will cancel out. So this is how it might look if I plugged all of those things in. So now we can see, based on what we just did, we've actually come up with part of the definition of a tangent line with slope m. Let's take a look at this function. This part right here is what we just came up with together. F of c plus delta x minus f of c over delta x. Now notice that I've added in the limit as delta x approaches 0. So why is that important? Well, let's think about our last picture, and this was our point c comma f of c, and then we were talking about some other point that we were going to use. So we might have started here, and then we said, okay, well, let's move that point a little bit closer, and then, hey, let's move that point a little bit closer, and delta x refers to the change in x. So as delta x, which for my yellow point would be from here to here, would be the distance of delta x. For my blue point, it would be a distance from here to here. So as you can see, delta x is getting smaller. For my red point, this guy is delta x. So this is just saying, as delta x gets smaller, as it approaches 0, so if I were able to put one, let's see if I have any other colors, really, really close, well, now I'm getting closer and closer and closer to 0 as a distance between f of c comma f of c, and my other point. Now notice it's just approaching 0. It's not exactly 0, because if the distance were 0, it would just be the same point twice and we can't find the slope. So this is the definition of a tangent line, and this is super duper important. So what I'm looking for here is, again, to use this definition to find the slope of the tangent line, because that's what this is going to do for us. And as you can see, this is the same function that we came up with earlier. Let me kind of point out where things happened here. This h is the same as delta x. So in our past examples, we've had delta x for all three of those positions, and now we're using h. You might see it either way. Both ways are completely normal and common in calculus, so I wanted to show you both. I also wanted to show you where the 2 came from, because we are looking for the slope of the line tangent to this function at 2, 1. So notice I'm plugging in x, whatever my x value is. So this is method 1, which is using direct substitution with that 2. So essentially what this is telling me to do is to find this function, and I'm going to find f of 2 plus h. So remember, that would just be 2 times 2 plus h minus 3. And then I'm going to subtract f of 2, and f of 2 would just be 2 times 2 minus 3. And so that's where my first step comes from, and you don't have to write this out, but that's where my first step came from. And I just want you to notice that this I replaced with all of this. Whoops. I replaced with all of this. And that f minus 2, or sorry, f of 2 I replaced with all of this. Keep in mind there's a subtraction in between, and that's why it was important for me to keep this in brackets or parentheses, either one, so that you knew that I'm subtracting the entire thing. From here, it's really just algebra, but I do want to point out to you that I'm going to continue to write the limit as h approaches 0 until I'm able to directly substitute in 0 for h to find the limit. And as you can see, I couldn't have done it here, because if I plug in 0 as the denominator, I'm dividing by 0 and it's undefined, and that continues to be the case. So as soon as I'm able to somehow reduce so that h is not in my denominator, then I'm going to use direct substitution. So let's take a look at my next step. Again, this is just simple algebra. I'm distributing, I'm rewriting. Keep in mind that was a minus that I distributed. Then I'm going to continue to simplify because I have a plus 4 and a minus 4 and a plus 2, a minus 3 and a plus 3. So that gave me 2h over h, and again, I have to keep writing this because I haven't been able to get rid of that h yet. Now notice on my next step, I got rid of those h's, so now I'm finding the limit as h approaches 0 of 2, and what's my solution going to be? My solution is going to be 2, because there's no place left for me to plug in a 0, which sometimes will happen, and sometimes we'll have a place to plug in a 0, but it won't make it undefined, so it's okay. So that's essentially how we're going to go through it. It's really just a lot of algebra. So that was method 1 using direct substitution. Now let's take a look at another way. So let's look at another example together, and honestly, if I were doing this particular question, I would just use method 1 the way we just went through it. However, I'm going to show you method 2, and method 2 is what I would use if they gave me more than one point at which to find that it's tangent. So we're just going to make it a little more general, and then at the end we'll plug in a value. So here's how I would do this. Notice on my last example I had the x value right here, so I would have -1 instead of c. Notice this time I'm just using c because c is more general, c being whatever that point is. And so I'm going to start by doing the same thing I did last time. This one's just going to be a little bit, there's just going to be more symbols because I have more variables. Instead of a -1, I have a c. But really it's the same thing. This is x squared plus 1, and this is x squared plus 1, my x in this case being c. Then I'm just going to do some simplification. Keep in mind that this guy, I know you're in calculus, so I don't have to tell you this, but I'm going to tell you anyway, is c plus h, c plus h. So I'm foiling. So that gives me the c squared plus 2ch plus h squared, if I FOIL that out. And then notice minus c squared minus 1. Then I look for things that I can reduce. C squared and minus c squared cancel, plus 1 and minus 1 cancel. And that gives me 2ch plus h squared over h. Obviously I can see I should be able to factor an h out of both terms in my numerator, leaving me with this, which of course would let me cancel out those h's. So now I have the limit as h approaches 0 of 2c plus h. Now I can directly substitute in 0, so this can be plus 0. So this is 2c plus 0, which means my answer is 2c. However, I have not answered the question that was asked. So I did a lot of work, but I haven't answered the question that was asked. The question that was asked is, what is the slope of the line tangent to f of x at -1, 2? Well, now I can say the slope is 2c, where c is whatever my x value was. So my slope is -2. So again, you might be thinking, well, that's stupid because I just did all that work, then I had to actually do extra work. But in my next example, you'll see where method 2 might come into play and be an easier method. So again, in our last example, we looked at this exact question, and we came up with this limit being 2c. And we already kind of looked at this one, but notice I can plug in any point that I want, and all I have to do is take 2 times whatever the x value is. So on that first one, our c is 0, since our x value is 0. So my slope at the point 0, 1 is 0. And we already know that our slope at the point -1, 2 is -2. I could give you 8 other points, and again, this is where method 2 would come in handy because I don't have to keep doing the work over and over. I do the work once and then keep replacing c with my x value. So let's take a look at our first example that I want you to try on your own. Press pause. There's 2 questions for you to try. When you're done, press play to see how you did. So for my first question, I would probably just use method 1 because they've given me a specific x value and just one of them, just 6. So again, I would start by taking 6 plus h and 6, And again, if you want to use delta x there, you can. It just tends to get a little cumbersome with all the delta x's. Then all I did was start doing the math. So I'm using 3x minus 5. I start distributing, combining like terms, etc. Of course, I didn't show quite as much work because I was trying to make it fit on a half of a page. But when I get to the end, I should end up that 3h over h, which of course cancels, which means my limit is 3, which means that the slope of the tangent line at the point 613 is 3. For my second example, I would use method 2. And for method 2, again, I'm going to use c instead of 2 or 3. And I'm going to simply just find whatever it is, and it turns out to be 2c. So find whatever my slope is in general in relationship to x that I'm plugging in. And then, of course, I would plug in the x values of 2 and 3 to find my solutions of 4 and 6.